For my independent science research project, I did an experiment called The Effects of Alcohol and Protein on Beer Foam Half-Life by me, Sammy Bartlett. I became interested in this topic when I saw soda being poured. When soda is poured, it foams up. The foam is caused by carbonation that goes away after a couple seconds. But then I saw a beer being poured and noticed how the foam was created. When a beer is poured, the foam stays a lot longer, so it can't only be caused by carbonation. So how is beer foam created, and why does it last so long? I did some research and found out that the foam is made of carbohydrates, which have high and low molecular weights. The high molecular weight molecules were about 10% protein. This protein was called protein Z. Now the low molecular weight molecules are mainly protein, but it was a different type of protein. This protein was called lipid transport protein 1. The scientists that figured this out were able to use these proteins to recreate the foam. Knowing this about beer foam, how stable is beer foam? And are there things that affect beer foam in different ways? Beer foam half-life was the way I measured how stable beer foam is. Beer foam half-life is the amount of time it takes the foam to decrease by half, which tells you how stable the foam is. Alcohol is known to affect protein interactions and reduce surface tension. By knowing this, I can formulate a hypothesis. If alcohol is added to beer, then the foam will be less stable and cause a shorter half-life. We also know that foam is made of proteins, so I can formulate a hypothesis that if protein is added to beer, then the foam will be more stable and cause a longer half-life. After doing the research, I tried to find an experiment like mine on the internet, but couldn't. So instead, I decided to dive in headfirst to try to test it out. Along the way, I had some experimental challenges. My first experimental challenge was finding out that one bottle equaled one trial. I opened a bottle and poured a little beer into a graduated cylinder. I recorded the half-life, then used the same open bottle of beer and poured again. During the first test, the open beer bottle was losing carbonation, so the half-life for the second pour would not be the same as the first pour. To make sure they were all the same, I would have to wait the same amount of time before pouring each trial to reduce variability. Also, both trials didn't get the same amount of beer each time it was poured, so a whole bottle would need to be used so there would be less variability. My next experimental challenge was trying to reproduce a controllable pour. Everyone knows that when pouring a beer, you want to tilt the cup and the bottle to about a 45-degree angle and pour the beer down the side of the cup to not have it hit the bottom because otherwise it foams up too much. I created a set slant that would hold the bottle. We placed the bottle there and popped off the cap. Because of the pressure put on the cap at the downward angle, the foam exploded everywhere. Then I realized it's hard to get the same angle every time on the pour, so what if the bottle was just upended? When the bottle is upended, you have less variability and a consistent pour. Plus, the carbonation exhausted from the beer, giving you exactly the same amount of foam every time. My last experimental challenge was finding out that the container diameter affects the half-life. At the beginning of testing the experiment, we used a container called a yard of beer. It's in such a shape that there's a ball at the bottom and an exaggerated funnel on top of it, where the neck is skinny and long. When testing the control, we noticed that the wide part of the funnel, the foam decreases quickly. But when the foam gets to the skinny part of the tube, skinny tube part of the container, it took a lot longer for the foam to decrease. This is because the ratio of surface area to the container versus bubbles was greater because the skinny tube caused bubbles to touch more glass. This then increased the adhesion forces between bubbles and silicon dioxide in glass. So now the adhesion forces were greater than the cohesion forces, which is the force of attraction between identical molecules, which caused the bubble molecules to stick to the glass. I realized that I needed a container where the diameter stayed the same throughout. I found a 1-liter beer mug that would hold a whole bottle of beer and also all the foam it creates. At the beginning of the experiment, I tested the control to get a baseline to compare it to. First, I graduated a 1-liter beer mug. Then I opened a bottle of beer and waited 30 seconds. Once the 30 seconds was up, I upended the beer into the beer mug, trying to get the beer to hit the center of the bottom of the mug. I had to shake out the foam at the bottom to get the most accurate measurement. I then started the timer once it reached 900 milliliters and immediately marked the bottom of the foam. Using the top mark of the foam at 900 milliliters and whatever mark I got at the bottom, I was able to calculate the height of where the half-life would be, the half-life being half of the foam. I used that equation to calculate the half-life. Once the foam got to the half-life mark, I stopped the clock and recorded the time. Then I rinsed the mug and repeated to get 5 data points. The alcohol procedures were very similar to the control. The only difference was that I added 15 milliliters of alcohol into the beer in between opening the bottle of beer and upending the bottle into the mug. But everything else was the same. Like starting the timer once the peak is reached, marking the top and bottom of the foam on the mug, and then calculating the half-life height. And lastly, stopping the timer once the half-life is reached and recording the time. Then for the other independent variable, I added 300 milliliters of alcohol. 30 milliliters of alcohol. It was pretty much the same by adding 15 milliliters of alcohol into the beer bottle, but I also added 15 milliliters of alcohol into the beer mug because all 30 milliliters didn't fit into the top of the beer bottle. The alcohol at the bottom of the beer mug still mixes into the beer because when the foam hits the bottom of the mug, it moves around and mixes in. The protein procedures are similar to alcohol, but I had to prepare the protein first. For the first independent variable of 0.34 grams of protein, I whisked 1 tablespoon of 15 milliliters of wheat isolate protein powder into 195 milliliters of water. This makes 200 milliliters of protein solution with 4.5 grams of protein in it. So 15 milliliters of protein mixture equals 0.34 grams of protein. I then added the mixture into the beer between opening and pouring. For the 0.68 grams of protein mixture, I whisked 1 tablespoon of protein powder into 95 milliliters of water, making a more concentrated mixture. So 100 milliliters of protein is 4.5 grams of protein, so 15 milliliters of protein mixture equals 0.68 grams of protein. Now the data for the beer foam half-life comparing the control to adding the alcohol shows a decrease in half-life. On the y-axis is the time of the half-life, and on the bottom are all my independent variables, including the control, which is the first column, and then in the second is adding 15 milliliters of alcohol. Since the control, the actual beer we used had 5% alcohol, when we added 15 milliliters of alcohol, it increased it to 7.85% of alcohol in the beer, and as you can see, it decreases by a lot. But then when we increased it to 10.48% alcohol by adding 300 milliliters of alcohol, it decreased by a lot more, but the standard deviation increased by a lot because since it was so much alcohol, it wasn't always very reliable, or because it was such a big amount, and beer isn't supposed to have that much alcohol in it. That graph showed that the more alcohol added to beer, that means a shorter half-life, which then means a less stable foam. This data is for the beer foam half-life. Comparing the control to the adding of protein shows an increase in half-life. The same thing where the time of half-life is on the y-axis and all the independent variables are on the x-axis. The first one is the control, but then the next two are the adding of protein. So the beer that we used had 1.3 grams of protein in it, but when we added 3.4 grams, it made it 1.64 grams of protein, and then by adding 0.68 grams of protein, it made 1.98 grams of protein. And the same thing happened with when adding a lot of protein. The standard deviation increased a lot because it wasn't as reliable, and it varied a lot more because the beer doesn't normally have that much protein in it, so the molecules just didn't work out as well. That graph showed that the more protein that was added to the beer means a longer half-life, which means a more stable foam. My experiment proved that the more alcohol in beer, the less stable the head of foam will be. But the more protein in beer, the more stable the head of foam will be. Thank you.